So when you slide into the driver's seat of a modern electric vehicle and, you put your foot on the brake and press that start button, what exactly do you expect to happen?
Well, you expect silence, right? An instant, completely silent activation.
Right, exactly. The screens light up, maybe the climate control hums to life, and you're just immediately ready to pull out of the garage. But what you don't see, and frankly what automotive engineers spend literally millions of hours making sure you never have to see, is that behind that split second of silence, there is an incredibly violent electrical event just trying its hardest to happen.
Oh, absolutely. It's a remarkable illusion of simplicity. We tend to judge EVs on things like range or 0 to 60 times, but the sheer volume of defensive engineering going on just to wake the vehicle up safely is staggering.
It really is.
Mm.
I mean, we're talking about massive amounts of raw energy that, if left unchecked, would literally tear the internal components of your car apart before you even checked your mirrors.
Yeah, the forces the power conversion system has to wrangle are genuinely terrifying if you understand the physics.
And that's exactly what we're looking at today. Welcome to today's deep dive. We've got our hands on a stack of, well, highly technical engineering specifications dealing with high voltage and vehicle safety faults.
Right.
And we are going to zero in on one specific, universally dreaded scenario in the engineering world. It's a dual motor sequence failure that engineers categorize at the very top of the danger scale. I mean, it's called C03 pre-charge failure.
Yeah, the pre-charge sequence. To give you a sense of the stakes here, a failure in this specific sequence is classified under the ISO 26262 standard as an ASIL D fault.
ASIL D, that's the big one, right?
It is. It stands for Automotive Safety Integrity Level D. In functional safety, that is the absolute highest risk classification possible.
Wow.
We aren't talking about, your infotainment screen freezing. We are talking about the severe risk of catastrophic hardware destruction
Right.
or immediate loss of power at highway speeds, or, in the worst case scenario, a thermal event.
Which is just the polite engineering term for a fire.
Exactly. A very intense fire.
Okay, so let's ground this in a visual before we get into the heavy engineering. Because when I was parsing through our sources, an analogy just kept playing in my head. So imagine you have a massive, completely empty swimming pool.
Okay, I like where this is going.
Right, so in our electric vehicle, that empty pool represents the DC link film capacitors. These are basically giant, temporary energy storage tanks sitting right between your battery and your electric motors.
Correct.
Now, you need to fill that pool, but your only water source is a highly pressurized industrial fire hose. That fire hose is your 800-volt high-voltage battery pack.
Right, and if you just open the floodgates and blast that fire hose directly into the completely dry pool all at once.
The physical force of that water would rip the tiles off the walls. It would shatter the concrete. The force is just too much, delivered way too fast.
And that destructive blast of water translates perfectly to electrical physics. We call it inrush current.
Inrush current, right.
Yeah, when a vehicle has been sitting off, those capacitors are completely drained. They're empty. If you were to take an 800-volt battery and connect it directly to an uncharged capacitor via a solid metal contactor, the physics are brutal.
Because it just wants all the power immediately.
Exactly. For a fraction of a second, an uncharged capacitor acts indistinguishably from a dead short circuit. It demands an astronomical amount of current instantly to fill that vacuum.
And the battery is, I assume, more than happy to provide it.
Oh, it will dump everything it has. The resulting surge will punch microscopic holes straight through the silicon carbide power switches. It'll detonate the film inside the capacitors. And, most dramatically, the sheer heat of that massive electrical surge will physically melt the main high voltage relays.
Wait, like literally melt the metal?
Literally weld their middle contacts together permanently.
Man, we obviously can't just turn on the fire hose.
Yeah.
And that is where this vital pre-charge concept comes in. Going back to our pool analogy, instead of grabbing the fire hose, you first grab a standard narrow garden hose. You turn that on, and you slowly, gently stream water into the pool until it's about, 95% full. Once the water level is high enough, the pressure inside the pool is almost equal to the pressure inside the fire hose.
That's the equalization phase, yeah.
Exactly. And only then do you open the main valves. Because the pressures are equalized, the pool can handle the massive flow without any violent disruption. That garden hose, that is the pre-charge sequence.
Spot on. Mechanically, the pre-charge sequence routes the high-voltage electricity through a dedicated, highly resistive pathway. We call it the pre-charge resistor.
So it acts like a bottleneck.
Yes, it artificially bottlenecks the flow of current. It forces the DC link capacitors to charge up on a controlled, predictable curve over, well, just a few hundred milliseconds.
Right.
The entire engineering spec we're analyzing today revolves around one core question. What do we do when that garden hose process goes wrong?
And I want to break down how the industry tackles that terrifying question. Because from my reading of the materials, it seems like they attack it from 5 distinct angles.
Yes, it's a very multi-layered approach.
Right. First, they analyze the raw physics of how the failure happens. Second, they build a paranoid digital brain to catch it. Third, they try to redesign the blueprint so the physics can't happen in the first place. Fourth, they lock down the human assembly lines. And finally, they just torture the finished product to prove it works.
It is a textbook holistic defense strategy because you simply cannot solve an ASIL D hazard with a single line of code or a thicker piece of copper. It requires an interdisciplinary approach.
So let's start with the raw physics, Section 1. Before we can appreciate the defense mechanisms, we have to understand the physical threats looming inside that engine bay. And the sources outline 4 primary ways this garden hose sequence can violently fail.
Right, the physical root causes.
Exactly. The first one is simply the thermal fusing of the pre-charged resistor itself. It literally melts.
To understand why a solid piece of metal and ceramic would melt, we have to look at a thermodynamic principle called Joule heating.
Joule heating, okay.
The formula for this is current squared, multiplied by resistance, multiplied by time, or I squared RT.
Okay, I squared RT.
The crucial detail there is that the current is squared. This means if the current flowing through a circuit doubles, the heat generated doesn't double, it quadruples.
Oh, wow. And a resistor's entire job in life is just to create electrical friction, right?
Exactly. It's an intentional electrical bottleneck. And the inevitable byproduct of that friction is rapid, intense heating. Now, these aren't the tiny little colorful cylinders you might have soldered onto a board in high school physics.
Right, not the little plastic things.
No, we are talking about heavy-duty components. They are usually wire-wound ceramics or encased in thick aluminum housings. Their sole purpose is to absorb a massive shock wave of electromagnetic energy, convert it into heat, and survive.
And normally that works out fine because the sequence is so incredibly fast. The garden hose is only on for a fraction of a second, so it has plenty of time to cool off while you drive.
Yes, normally.
But the documentation highlights a fascinating and honestly very human-driven failure mode here. It basically implies that an impatient driver can melt their own car just by pushing the start button too many times.
Yeah, human operators are a massive liability if the software doesn't intervene.
That is wild.
Consider someone sitting in a parking lot. They press start, the garden hose activates, the resistor absorbs a massive wave of heat, and the car wakes up. Then the driver immediately changes their mind and turns the car off.
Okay.
A few seconds later, they realize they need to roll down a window. So they press start again. Another massive wave of thermal energy is dumped right into the resistor.
And because it's a physical object, it just takes time for that heat to dissipate into the air.
Precisely. The physical substrate has what we call a thermal time constant. It cannot shed heat as fast as the electrical current can inject it. So if the interval between those starts is too short, the residual heat compounds, the internal temperature, the junction temperature skyrockets past its limits.
So what actually happens inside the component when that happens?
The thermal stress breaches the physical limits of the conductive alloy. The internal wire winding will structurally fail and literally melt apart. Or, if there's a sacrificial thermal fuse built in, that fuse will blow to prevent a fire.
Either way, it breaks.
Yes. In either scenario, you now have a physical open circuit. The electrical pathway has been severed, your garden hose is permanently cut in half, and the vehicle is just dead in the water.
Man, okay, so that's physical threat number 1, melting the garden hose through thermal abuse. Threat number 2 is equally terrifying. The documents call it contactor welding and degradation. And this one feels insidious because the sources imply it might actually be caused by something that happened the last time you drove the car, maybe days ago.
Yes, we have to talk about the main contactors here. These are not solid-state transistors. They are giant, heavy-duty mechanical switches, thick copper or silver alloy plates that physically slam together to connect the battery to the drivetrain.
Right, and when you shut the car down normally, the current drops and these plates just pull apart cleanly.
But what happens during an abnormal shutdown? Say the car detects a crash or a severe fault while driving, and it has to kill the power instantly while hundreds of amps are still flowing.
Oh, right, because it's trying to save you.
Exactly. But this is where the physics of air come into play. Air is normally a great insulator, But if you try to pull two pieces of metal apart while massive current is flowing through them, the electricity doesn't politely start.
It wants to keep going.
Right. The voltage is so high, it literally tears the electrons off the air molecules between the separating plates. The air becomes ionized. It turns into a highly conductive plasma arc.
It's essentially lightning inside a plastic box.
A localized lightning strike, yes. And the temperature of that plasma arc can exceed 10,000 degrees Fahrenheit. It's identical to the physics of an arc welder used in heavy construction. So as those plates pull apart, that plasma arc melts the surface layer of the contacts.
I think I see where this is going. So if the metal is molten,
If the system tries to close them again quickly, or if the liquid metal pooling is severe enough as they separate, it cools and physically fuses the two sides together. This is pre-welding.
wow. So fast forward to the next morning. The driver gets in, completely unaware of this microscopic damage. They press the start button.
Right.
The car's computer says, okay, initiating safe garden hose pre-charge sequence. But because that main contactor is already physically welded shut from yesterday's plasma arc,
The garden hose is completely bypassed.
because the fire hose is already wide open.
Exactly. The instant the battery management system closes its negative relay to complete the circuit, that massive inrush current bypasses the resistor entirely. It blasts straight into the uncharged capacitors, frying any sensitive electronics and potentially damaging the battery pack itself.
And the sources also point out that it doesn't even take a dramatic arc welding event to cause problems, right?
Oh.
The smaller switch, the contactor that specifically controls the garden hose, can't just degrade over time.
Yes. Mechanical components in an engine bay undergo years of intense vibration, extreme temperature swings, and tens of thousands of cycles. The tiny electromagnetic coil that physically pulls the switch closed can suffer metal fatigue and snap.
Or they mention carbon buildup too.
Right. Even under normal conditions, microscopic arcing occurs every time a switch opens or closes. Over 10,000 cycles, those tiny sparks scorch the metal, leaving a microscopic layer of carbon soot on the surfaces.
And soot isn't a conductor.
Carbon is not a great conductor at all. A brand new contactor has resistance measured in mere milliams. Zero friction. But as that soot builds up, the electrical resistance of the switch skyrockets. It becomes an unintended resistor itself.
So it chokes off the flow of the garden hose, meaning the sequence times out before it can fill the pool.
Exactly.
Which flows perfectly into the third root cause. We've melted the hose, we've broken the valves.
Now let's talk about the pool itself.
Yeah.
Threat number 3 is a DC link short circuit. To keep our analogy going, this is basically a catastrophic leak in the swimming pool. A leak so massive that it defies physics to try and fill it.
Right.
In an EV, the DC link capacitor sits immediately upstream of the power semiconductor switches. These switches, silicon carbide MOSFETs or IGBTs, chop up the direct current from the battery into the precise alternating current waves that spin the motors.
And these silicon switches can fail in a very specific way, according to the document.
They switch thousands of times per second. If an IGBT gets hit with a voltage spike or thermal stress, the delicate crystalline structure of the silicon can break down. It suffers a shoot-through failure.
A shoot-through failure, what does that mean?
The semiconductor melts internally and forms a permanent, uncontrolled pathway straight to the ground.
It becomes a dead short.
Precisely. And it's not just the silicon. The documentation mentions busbar breakdown and stator winding insulation failure.
Okay, what's a bus bar?
A bus bar is a thick, rigid bar of solid copper or aluminum. It conducts massive currents where a standard wire would just melt. If the insulating tape between a positive and negative bus bar degrades, you get a hard short circuit. Same with the electric motor itself. It's full of tightly wound copper wire, the stator windings. If the thin enamel insulation on that wire flakes off from heat, bare copper touches the grounded metal casing.
So from the perspective of the pre-charge system, it turns on the garden hose. Electricity flows. But the voltage reading inside the capacitor never rises.
The water level in the pool stays at absolute zero.
Because every single drop of water you pump in is pouring straight out of a massive hole in the bottom.
The pre-charge current is bleeding away endlessly. The system's sensors monitor the voltage across the capacitor, which the spec denotes as UDC. If there's a severe short, UDC will remain stubbornly near zero no matter how long that garden hose is on.
And if the brain didn't catch it, it would just keep pumping energy until the resistor caught fire.
Exactly.
Which brings us to the fourth root cause. You and I were actually discussing this before we started recording, and you called it the sneakiest, most frustrating failure mode of all.
Oh, without a doubt.
Because it isn't actually a failure of the power system at all. It's a failure of the car's perception of reality. The document terms it AFE, sensing drift and leakage.
Right. AFE refers to the analog front end. An EV's microprocessor operates on tiny voltages like 3.3 or 5 volts.
Okay.
It cannot directly measure an 800-volt power line. Doing so would instantly vaporize the microchip.
I would assume so, yeah.
So engineers use a network of highly precise film resistors to step that massive 800-volt potential down to a safe, proportional 2-volt signal that the microchip can safely read.
So it's like a translator between the raw physical power and the digital brain.
But translators can become unreliable. These sensing resistors sit in an engine bay exposed to extreme heat. Over time, that prolonged exposure to heat causes a phenomenon called thermal drift. The physical resistance value of the component subtly shifts.
So a resistor that was exactly 10,000 ohms at the factory might drift to 10,050 ohms after 2 years.
Right, which means the math the translator is doing is suddenly wrong.
But the document also highlights a much more insidious, microscopic problem related to moisture.
Yes. The power electronics are housed in thick metallic casings sealed with rubber O-rings. But through thousands of thermal cycles, those O-rings experience thermal fatigue. They microcrack. And in high-humidity environments, microscopic moisture vapor seeps inside.
I don't have an engineering degree, but I know water and 800-volt electronics don't mix well.
No, they don't. It initiates a destructive chemical process called electrochemical migration, or ECM. When you have a high voltage differential across a printed circuit board and you introduce microscopic moisture, the water acts as an electrolyte.
Okay, so what does that actually do?
It starts dissolving the metallic solder on the circuit board itself, usually the silver or tin at the positive terminal.
Dissolving the metal on the board.
On a microscopic level, yes. The metal ions migrate through the moisture toward the negative terminal. And as they reach the negative side, they deposit themselves and start growing into tiny, tree-like conductive filaments called dendrites.
Wait, they grow like metal trees?
Yes, over months or years, these microscopic metal trees grow across the surface of the circuit board until they bridge the gap between two sensory traces.
They literally build their own microscopic wires. That is crazy.
Exactly. And these unintended dendrite wires create tiny electrical leakage paths. The voltage meant to reach the microchip bleeds away across the damp circuit board.
This is what I meant when I compared it to a rusty fuel gauge.
It's a perfect analogy.
The actual physical power system, the swimming pool, is completely fine. The capacitor has safely charged up to 95%. The contactors aren't welded, the resistors aren't melted. But because the sensing resistors have thermally drifted, or because a metal tree grew across the board, the software is receiving corrupted data.
It reads a false low voltage. The microprocessor looks at its rusty fuel gauge and deduces, the capacitor voltage is hovering near zero. I must have a catastrophic short circuit.
And it declares an ASIL D failure and aggressively locks down the entire vehicle.
Even though the hardware is perfectly healthy, it protects the driver based on bad information.
Man. So we have these 4 massive physical threats constantly hovering over that fraction of a second when you turn the key. Thermal fusing, contactor welding, dead shorts, and sensory drift.
Right.
With all that potential chaos, how does the car's brain actually catch these faults before the hardware destroys itself? This leads us out of the physics and into the software. Section 2. The digital shield.
To understand the digital shield, we first have to establish the ground rules of functional safety timing. The core metric here is the FTTI.
FTTI, okay.
The fault-tolerant time interval. When an ASIL D fault occurs, the FTTI is the absolute maximum window of time the system is allowed to exist in a failed state before permanent hardware damage occurs.
And what is that window for a pre-charge failure?
The engineering consensus sets that FTTI at a blistering 60 milliseconds.
Let me just stop you there to put 60 milliseconds into human perspective. A rapid eye blink takes about 300 milliseconds.
Oh, okay.
The stroke of a car engine running at highway RPM takes roughly 20 milliseconds. The car's computer has less than a quarter of the time it takes you to blink to recognize the garden hose is leaking, double-check its math, and trigger a system-wide lockdown.
It is a phenomenal synchronization of software and hardware. And the architecture doesn't achieve this by waiting until the end of the sequence to see if things worked out. It utilizes a proactive, multi-layered diagnostic strategy.
Okay, what's the first layer?
It's a mathematical algorithm called dynamic slope monitoring. It focuses on the rate of change of the voltage. In calculus terms, this is du/dc over dt.
So the system flips the garden hose switch on. What exactly is the software looking for in those first few milliseconds?
It's analyzing the geometric shape of the voltage curve. When a healthy capacitor charges, the voltage doesn't jump instantly. It rises on a predictable, steep curve. The microcontroller is continuously calculating the slope of that rising curve in real time.
Right.
The specification mandates a critical checkpoint within the very first 50 milliseconds of the sequence.
Wait, it doesn't even wait the full 60-millisecond safety window.
It cannot afford to. If there is a massive downstream short circuit, a giant hole in our pool, the voltage curve will not rise. The slope will remain completely flat or near zero.
Okay.
If the software calculates a flat slope at the 50 millisecond mark, it deduces instantly that a severe leak exists. It proactively aborts the pre-charge sequence right then and there.
It's like turning on the hose, looking at the pool for one single second, seeing the water pouring out a drain, and immediately shutting off the valve rather than standing there for an hour hoping it magically fills up.
That is the exact logic, and it serves a critical protective function. By aborting early based on the slope, the system prevents the pre-charge resistor from having to absorb the remaining duration of short-circuit current. It effectively saves the component from melting down.
That is incredibly smart. But let's say the slope looks good, the voltage is rising, the pool is filling. The system still has a hard deadline, right?
Yes. Depending on the battery chemistry and capacitance, the system defines a maximum allowable pre-charge time, frequently around 200 milliseconds.
Okay.
If the sequence is still running at that deadline, the software executes the second diagnostic, the voltage delta check.
Ah, so it does a final math problem to make sure the pressures match.
Exactly. It takes the total available voltage of the high-voltage battery UBAT and subtracts the voltage currently stored in the capacitor UDC. It's checking the differential gap.
And if the garden hose did its job, those numbers should be nearly identical.
The rule encoded in the spec is strict. If the gap between the battery voltage and the capacitor voltage remains 20 volts or wider at the 200 millisecond deadline, the system definitively fails the sequence. It concludes the capacitor simply didn't cross the required 95% charge threshold.
Okay, but I'm seeing a blind spot here. We talked earlier about how the main contactor could be physically welded shut from a plasma arc.
Right.
How does the software actually know what the physical metal is doing? Because the software can send a digital command saying, open the switch, but if the metal is welded solid, the command is meaningless.
That is a fundamental vulnerability in embedded systems. Software commands are invisible. You must have physical, mechanical confirmation.
How do they get that?
The industry solves this with the third defensive layer: auxiliary contacts plausibility checks. These high-voltage contactors are not just single dumb switches. They are complex assemblies that include tiny, secondary low-voltage switches physically linked to the main moving armature.
Oh. So when the massive heavy metal bar slams shut to connect the 800 volts, its physical movement also depresses a tiny low-voltage pin that sends a simple on-off signal back to the computer.
It provides absolute mechanical truth. The software relies heavily on this feedback loop. When the microcontroller sends the digital command to close the relay, it simultaneously starts a rigorous 10-millisecond timer.
Okay.
If it does not receive the low-voltage return signal from that auxiliary pin within 10 milliseconds, the software flags an immediate hardware incongruity.
The software says, I yelled close, but the physical hardware is refusing to tell me it closed. Something is jammed.
And it locks down. Conversely, before the sequence even initiates, the software checks that pin. If it reads that the auxiliary contact is already in the closed position when the car has been supposedly off all night,
It knows instantly that the main contactor is welded shut from yesterday.
exactly, it will flatly refuse to begin the startup sequence, isolating the battery entirely.
This architecture sounds bulletproof. But reading through the document, I hit a concept that genuinely baffled me for a minute. The spec describes the digital processing unit as a Dewar-Checker dual-core setup.
Ah, yes, the Dewar-Checker architecture.
Right. It details how there's a main microcontroller core doing all the calculus, checking the slopes, managing the timers. But then it mandates a second, completely separate digital brain running right alongside it, doing the exact same mathematical homework at the exact same time. Why on earth do we need two brains doing redundant math?
Welcome to the deepest, most paranoid levels of functional safety engineering. To achieve an ASIL D rating, you have to defend against the statistically improbable. We are defending against a quantum-level phenomenon known as a bit flip.
A bit flip, like a literal one turning into a zero deep inside the computer memory.
Yes. A microcontroller processes data in registers, which are microscopic arrays of transistors holding a tiny electrical charge to represent binary ones and zeros. An EV engine bay is a hostile environment. Extreme heat, electromagnetic interference, and crucially, high-energy cosmic background radiation.
Wait, cosmic rays. We are designing cars to survive radiation from deep space. That sounds like science fiction.
It is a documented, unavoidable statistical reality in modern microelectronics. It's known as single-event upsets. High-energy neutrons generated by cosmic rays hitting the upper atmosphere constantly shower the Earth.
Okay.
If one of these particles happens to strike the specific microscopic transistor holding a data bit, it can inject enough energy to spontaneously flip that transistor state from a 0 to a 1, or vice versa.
So if that rogue cosmic particle happens to hit the exact memory address where the computer is currently storing the capacitor's voltage reading.
The main processor, the doer core, might suddenly believe the capacitor is sitting fully charged at 800 volts, when in physical reality, it is completely empty.
Oh my God.
Operating on this corrupted data, the doer core would cheerfully command the main contactors to slam shut right into a dead short circuit, totally blind to the catastrophe it just caused.
Because its brain was literally altered by a subatomic particle for a microsecond. That is both fascinating and terrifying.
Which is precisely why the standard mandates the checker core. This is a completely independent processing unit. It's physically segregated on the silicon die. It often runs a differently compiled version of the software to prevent identical systemic bugs.
Right, so it doesn't make the same mistakes.
Exactly. The checker core utilizes its own entirely separate analog-to-digital converter channels. It calculates its own dynamic slopes, it runs its own voltage delta checks, and thousands of times a second, the doer and the checker must compare their math.
I calculate we have 400 volts. What do you calculate? I also have 400 volts. Proceed.
Precisely. But if the doer says the voltage is 800 and the checker says the voltage is 0, the specification actually demands intervention if there is a discrepancy of greater than just 5 volts between their calculations.
Just 5 volts. That's a tiny margin. What happens? Do they argue about it?
There's absolutely no time to argue. The document outlines that a dedicated independent silicon module, often called the Safety Management Unit, or FCCU, steps in. It physically bypasses the software entirely.
Oh.
In under 100 microseconds, it severs the low-voltage power supply feeding the physical relay drive circuits.
Wow. It doesn't ask the software to gracefully shut down. It reaches over and physically unplugs the power, steering the hardware.
It acts as an absolute hardware override. By cutting the drive power, it guarantees the high-voltage contactors drop open and default to a safe, unpowered state. It completely neutralizes the risk of a software control escape caused by a stray cosmic ray.
Okay, so the digital shield works. It catches the flat slope or the mismatched voltage or the bit flip, and it shuts the sequence down safely.
Yes, it isolates the danger.
But let's loop back to the human element. The impatient driver who keeps mashing the start button, building up physical heat in the resistor. If the software shuts the car down, what stops the human from just immediately pressing the button again and trying to force it?
This is the final piece of the digital shield, active thermal isolation. The software engineers understand human psychology. When a pre-charge failure is detected and aborted, the system doesn't just throw a generic check engine light.
Okay, what does it do?
It actively models the thermodynamic reality of the hardware. It utilizes a thermal accumulator model.
So it builds a mathematical model of how hot the physical resistor is getting in real time.
Exactly. By tracking exactly how much current flowed and for how many milliseconds before the abort occurred, the software calculates the estimated internal junction temperature of the resistor.
Okay, that makes sense.
Crucially, it then writes that calculated temperature value into non-volatile memory.
Non-volatile memory, meaning even if the frustrated driver pops the hood and disconnects the 12-volt battery to try and force a hard reset of the car's computers,
the car will not forget. When power is restored, the system reads that non-volatile memory and says, I remember exactly what you did, and I know exactly how hot my components still are.
Oh, that's brilliant.
The system enters a hard, uncompromising lockout state. It will physically refuse to accept the start command from the user.
It basically grounds the driver.
It actively calculates a theoretical cooldown curve based on ambient temperature sensors. It will enforce this lockout for anywhere from 10 to 30 seconds, strictly until the digital model guarantees that the physical core of the resistor has cooled safely below 50 degrees Celsius.
It entirely removes human impatience from the safety equation.
Yes. It assumes the driver cannot be trusted.
The level of digital paranoia is just astounding. I love it. But as complex as catching a fault in 60 milliseconds is, the pinnacle of engineering isn't just about reacting to a problem. It's about ensuring the problem is physically impossible to begin with.
Which brings us to the design phase.
Exactly. Section 3, DFMEA. The Design Failure Mode and Effects Analysis. This is where engineers stare at the blueprints and try to design the danger out of existence.
DFMEA is the foundational bedrock of reliability. It's the practice of looking at a theoretical design on a screen and asking, how will physics try to destroy this, and how can I overbuild the material to prevent it?
Right. And the first major countermeasure here addresses the thermal fusing of the resistor we discussed earlier. It is a strict mandate on component sizing. This was the part of this book where the math just blew me away.
The safety margins are significant.
They are extreme. The formula dictates that the energy rating of the chosen resistor must be greater than or equal to 3 times the maximum possible energy the capacitor can hold. 3 times.
Let's unpack the physics behind that formula. The total kinetic energy stored in a fully charged capacitor is calculated as 1/2 multiplied by the capacitance multiplied by the voltage squared.
Right, the max energy.
The spec mandates that whatever that maximum theoretical energy blast equates to in joules, the physical mass of the resistor must be large enough to absorb 3 full consecutive impacts of that energy without approaching its melting point.
It's like requiring a bulletproof vest to stop 3 point-blank rounds to the exact same spot without flinching.
That's a good way to put it.
But it isn't just about the sheer size of the resistor, is it? The document is very specific about the materials and how it's mounted. It insists it cannot be a standard component just soldered floating on a circuit board.
No, the material specification is non-negotiable. It mandates an aluminum-housed resistor.
Why aluminum?
Aluminum has exceptional thermal conductivity. Furthermore, the design rules dictate that this flat aluminum housing must be physically compressed tightly against the large cast metal chassis of the power conversion system itself, usually with a layer of thermal paste in between.
Oh, so they use the entire car part as a heat sponge.
Exactly. They drastically slash the thermal resistance path. By coupling it to the chassis, the entire massive metal body of the inverter becomes a giant heat sink for that single component. It rapidly pulls the destructive heat away from the sensitive internal ceramic windings almost instantaneously.
Okay, so they've overbuilt the physical hardware to handle the heat.
Mm-hmm.
But what about the sensory drift? We talked extensively about the rusty fuel gauge problem, the AFE sensing drift, where the software makes a bad decision because the sensing resistors physically changed their resistance when they got hot.
Yes, thermal drift.
How do you draw a blueprint that stops physics from altering the components?
You solve it through aggressive supply chain mandates. You outright forbid the use of standard commercial-grade electronics in the sensing pathway.
The DFMEA document explicitly mandates high-precision components.
Specifically, they require the use of Class 1 COG dielectric ceramic capacitors and ultra-high-precision thin-film resistors.
The specs listed for these resistors are wild, a 0.1% precision tolerance.
That means the manufacturer guarantees the physical resistance value of the component is accurate to within 1/1000th of its stated value, right off the factory floor.
That is incredibly tight.
But precision isn't enough. Stability is what matters. The critical metric the document enforces is the temperature coefficient of resistance, or TCR. It mandates a TCR of less than or equal to 25 parts per million per degree Celsius.
I need you to translate 25 parts per million into something tangible. If I'm driving through the desert in July, what does that actually mean for the car's brain?
Let's assume the ambient temperature inside that sealed metal engine casing increases by a massive 100 degrees Celsius, which is a brutal thermal swing.
Yeah.
Even under that extreme heat, a component with a 25 ppm TCR will alter its physical electrical resistance by a maximum of only 0.25%.
That is virtually nothing.
It renders the component functionally immune to thermal drift. By mandating these expensive, ultra-stable components at the bill of materials level, the engineers physically eradicate the rusty fuel gauge failure mode before the car is even built. The software can implicitly trust the incoming voltage data, regardless of the environmental extremes.
That is so cool. Now, as I was reading through the blueprint section, I found a design feature that I thought was absolutely brilliant. It's called reverse freewheeling gating.
Ah, yes.
Can I try to explain this using a new analogy, and you tell me if I'm understanding the physics correctly?
Please do. I'd love to hear it.
Okay, so the entire purpose of the pre-charged circuit is to act as a controlled pathway for electricity to flow forward from the high-voltage battery through the resistor to fill up the capacitors.
Correct.
But what happens if you are cruising down the interstate at 80 miles an hour and something upstream suddenly trips offline? The massive electric motors connected to the wheels don't just instantly stop spinning. They are still rotating at thousands of RPMs.
Because of the kinetic momentum of the vehicle, yes.
Right. And spinning magnets inside copper coils create a generator. Suddenly, the wheels are forcing the motors to generate a massive chaotic wave of high-frequency alternating current that pushes backward toward the battery.
Your grasp of the physics is excellent. We call that phenomenon back EMF, or reverse electromotive force. It is an incredibly powerful, highly chaotic wave of reverse voltage.
Right. So if that chaotic wave of back EMF surges backward into the precharged circuit, it would blast the precharged resistor from the wrong direction.
Which it is not designed to handle.
Exactly. It's designed for a smooth DC charge, not chaotic AC pulses. It would suffer what the document calls secondary electrical overstress and basically explode.
Yes, it would.
So to prevent this, the engineers install a massive high-voltage diode in series with the pre-charged resistor. And I think of the diode like a heavy, one-way security turnstile at a stadium.
The security turnstile is an apt metaphor.
The diode allows the calm, controlled direct current from the battery to push through the turnstile and flow forward during startup. But the instant that chaotic back EMF tries to surge backward from the spinning motors, the diode acts like a locked steel door.
It blocks it completely.
It completely blocks the reverse flow of current and ensures the pre-charged circuit can never, ever be hit from behind.
It is a supremely elegant, purely passive hardware defense. It requires zero software intervention, no sensors, no millisecond timing algorithms. It is a physical, immovable barrier engineered directly into the blueprint to prevent a highly specific, highly destructive edge case scenario.
So we had this theoretically perfect blueprint. The DFMEA has anticipated the extreme heat, the microscopic drift, the reverse voltage spikes. On a computer screen, the design is bulletproof.
On a screen, yes.
But blueprints don't drive on the highway. Physical objects do. And as we transition into the manufacturing phase, we hit reality. Because if the human worker or the robotic arm assembling this perfect design on the factory floor makes a tiny fraction of a millimeter mistake, all that brilliant theory falls apart instantly.
It absolutely does.
This brings us to Section 4, PFMEA, Process Failure Mode and Effects Analysis, the assembly line imperative.
This is the phase where engineering hubris meets the gritty reality of the factory floor. You can design the perfect aluminum heatsink and mandate extreme thermal coupling. But if the line worker simply forgets to tighten the bolt, holding it down quite enough,
everything melts. And that leads right into the torque angle servo bolting requirement in the text. This fascinated me because it proves that in the world of high-voltage engineering, tightening a bolt is not just tightening a bolt. It is a strictly controlled, highly traceable mathematical operation.
It must be. Consider the high-voltage bus bars and the relay terminals inside the casing. These metal connections must seamlessly pass hundreds of amps of current. If a bolt holding two copper bus bars together is even marginally loose, the microscopic physical contact area between the metal plates is vastly reduced. This creates tiny gaps, which dramatically increases the physical contact resistance at the joint.
And as we learned with Joule heating at the beginning, resistance multiplied by massive current equals massive heat.
Exactly. A loose bolt on a high-voltage terminal effectively becomes an accidental, uncooled pre-charge resistor. It will get incredibly hot, it will melt the plastic terminal housing around it, and it will inevitably cause a catastrophic arcing fire.
To absolutely prevent this human error, the manufacturing process mandates the use of data-traceable torque angle servo guns. These are not standard pneumatic wrenches, right?
No, not at all. They are precision robotic tools that measure not only the rotational force applied, but precisely how many degrees the bolt rotates during the tightening process.
But the control process goes even deeper than the robotic wrench.
Yeah.
The document states the factory uses OCR optical character recognition cameras to visually inspect every single bolt as they arrive on the assembly line.
Yes, automated visual inspection.
They're specifically looking to guarantee that every bolt has a phosphate coating. Why on earth does the microscopic chemical coating on the thread of the bolt matter to the electrical safety of the car?
It comes down to standardizing the coefficient of friction. The phosphate coating acts as a dry lubricant on the threads.
Okay.
If a bolt is dry or has inconsistent threading, the servo gun might read a high torque value simply because the metal threads are grinding and binding together. This leads the system to believe the bolt is tight, even though it hasn't actually clamped the metal plates down with sufficient force.
Oh, It's a false positive on tightness.
Precisely. By using OCR to mathematically guarantee the presence of the phosphate coating and coupling that with the torque angle servo gun, the factory engineers can mathematically guarantee that the axial clamping force, the actual downward physical pressure squeezing the plates together, is 100% to specification.
And the end goal of that obsessive clamping force is a very specific parameter in the document. A physical contact resistance of less than or equal to 5 milliamps, 5 thousandths of an ohm. They're guaranteeing at a factory-wide level that there is virtually zero electrical friction at these critical joints.
It seems obsessive, but an ASIL D hazard demands nothing less. Now, moving past the heavy mechanical assembly, the PFMEA also rigidly dictates how they handle the digital calibration on the line.
The end-of-line calibration station.
Yes, the EOL station.
This connects perfectly back to those ultra-precise components we talked about in the design phase. Even with 0.1% precision film resistors, the engineers still don't entirely trust the assembled analog circuit until it proves itself.
Because analog circuitry always possesses inherent microscopic variations. The exact thickness of the copper traces on the circuit board, the microscopic amount of solder used at the joints, the slight variance in the microchip, all of it aggregates into a tiny bit of systemic error.
It adds up.
It does. To eradicate this final margin of error, at the very end of the assembly process, an automated factory rig physically connects to the unit and injects a highly precise laboratory-grade reference voltage directly into the pins.
The specification notes they inject exactly 400 volts or 800 volts from a highly calibrated external power supply.
Yes. They inject a flawless 800-volt signal. The unit's internal microprocessor reads that incoming signal. If the car's computer says, "I am reading 798 volts," the factory rig knows the analog translation circuit is structurally off by 2 volts.
Okay, so it finds the error. Then what?
The rig's software then computes a dynamic gain and offset mathematical correction factor and permanently flashes that unique correction directly into the non-volatile memory of the vehicle's computer.
It custom calibrates every individual car's brain to perfectly map the microscopic quirks of its own physical hardware. That is so cool.
And the most vital safety aspect of this process is what happens if the unit fails the calibration check.
If it's too far off.
Right. If the required correction factor exceeds a predetermined limit, it indicates that a physical component has drifted dangerously outside acceptable manufacturing bounds. In that scenario, the manufacturing execution system, the central software running the factory, automatically locks the workstation.
It just stops the line.
It physically prevents the conveyor from moving that unit forward. It guarantees a unit with a compromised analog sensing circuit cannot be shipped to a consumer.
Okay, the mechanical bolts are perfectly torqued, the software is custom calibrated, but then I hit the next manufacturing control in the document, and I admit, I had to stop and reread it to make sure I wasn't misunderstanding the text. It states they use 3D X-rays on the circuit boards. Are they genuinely giving medical-grade CK scans to the electronics?
They absolutely are. The technology is called AXI, or Automated X-ray Inspection, and they frequently combine it with SAM, Scanning Acoustic Microscopy, which uses ultrasonic sound waves to look inside solid objects.
What are they so desperately looking for inside a drop of metal? The text mentions voiding limits.
When a factory oven melts solder paste to attach a component, the intense heat can cause chemical fluxes within the paste to vaporize. This creates microscopic bubbles of trapped gas inside the liquid metal before it hardens.
Okay, air bubbles.
These trapped gas bubbles are called voids. If a void is too large, it severely weakens the structural integrity of the solder joint.
I understand why a weak joint is bad, but why is it an ASIL D critical safety issue specifically for the pre-charged sensing circuit?
Think about the brutal physical environment an automotive circuit board lives in. It is subjected to years of intense, high-frequency kinetic vibration from potholes, from the suspension, from the rotational force of the motors.
Constant shaking.
Right. If there's a large trapped bubble of air inside a critical solder joint, say the joint connecting one of those ultra-precision voltage sensing resistors, that kinetic vibration will concentrate mechanical stress directly around the edges of the void.
Oh no.
Over thousands of miles, a microscopic fracture will begin to form and propagate through the solder.
And suddenly, while I'm cruising at 75 miles an hour down the highway, that microscopic crack expands just enough to momentarily sever the electrical connection.
The physical connection breaks for a single millisecond. The car's microprocessor suddenly reads 0 volts from the high-voltage system.
And it thinks the pool is empty.
Relying on its programming, it immediately triggers a false undervoltage fault. It concludes the pre-charge or the main battery has catastrophically failed, and it aggressively shuts the entire high-voltage drivetrain down at highway speeds.
And all of this happens because of a microscopic bubble of trapped air in a bead of metal formed 3 years ago on an assembly line.
That is exactly right.
That is mind-bending. So to prevent that hyper-specific nightmare, the 3D X-ray scans every critical joint on the board, and the rules laid out in the spec are incredibly stringent.
Very strict.
It mandates that total voiding in a single joint must be less than or equal to 5% of the overall volume, and no single individual bubble can be larger than 1%. If an air bubble measures 1.1% of the volume, the AXI machine flags it, pulls the entire board off the line, and throws it in the scrap bin.
The level of automated quality control is absolute. Because a failure at this level doesn't just result in a broken radio or a flickering screen, it results in a sudden, terrifying loss of motive power on a busy interstate.
So we've designed it flawlessly on the blueprint. We've assembled it perfectly using robotic wrenches and X-ray vision. Now, the engineering team takes these pristine, mathematically perfect units off the line, and they actively attempt to destroy them to prove they are ready for the consumer.
Yes, the destruction phase.
This brings us to the final section, DVPNR, or the Design Verification Plan and Report, the torture testing.
The DVPNR phase is where engineers seek to prove that their elegant mathematical models and their obsessive assembly line controls actually hold up against the brute, unforgiving force of physics. You don't just test if a unit works perfectly once. You test if it works perfectly 1,000 times in the most hostile environments imaginable.
And the first torture test the document outlines is the extreme repetition test. This addresses the impatient driver scenario head-on. They hook the unit up to a massive dynamic test bench pushing a full 800 volts of raw direct current, and they force the software to execute 1,000 continuous pre-charge and discharge cycles.
And the most critical parameter of that test is the time gap between the cycles. They set the interval to the absolute minimum safety threshold permitted by the software, which the document notes is a mere 10 seconds.
10 seconds. So they blast it with an 800-volt surge, wait 10 seconds, blast it again 1,000 times in a row.
They are intentionally trying to overwhelm the thermal mass of the aluminum resistor and the cooling block. They want to see if the heat will compound rapidly enough to melt the core.
But wait, remember the active thermal isolation we discussed? The digital memory model that locks the driver out.
Yes.
This brutal test proves that the software intervention actually works in physical reality.
Exactly. The acceptance criteria for passing this test are frankly brutal. After surviving 1,000 extreme cycles, the physical impedance, the resistance value of the resistor, cannot have drifted by more than 0.5% from its original state.
And the software must have flawlessly intervened every single time the temperature approached the critical threshold, locking the system out before irreversible hardware damage occurred.
It empirically proves the digital shield successfully defends the physical hardware from sustained, deliberate abuse.
But the abuse escalates significantly from there. The next validation combines mechanical kinetic torture with extreme thermal shock. This one reads like a test protocol for a lunar lander.
It's intense.
They mount the power conversion unit to a massive multi-axis shaker table, and they apply an ISO standard random vibration profile. The document specifies an acceleration force of 35 meters per second squared.
To give you a visceral sense of scale, the standard acceleration of Earth's gravity is 9.8 meters per second squared.
So it's more than 3 Gs.
They are subjecting this box of sensitive electronics to violent, chaotic, multi-directional shaking at roughly 3.5 times the force of gravity, continuously sweeping across a wide acoustic spectrum from 10 to 2,000 hertz. It simulates driving a vehicle over the worst, most deeply rutted washboard dirt road imaginable at high speeds.
But they aren't just shaking it in a comfortable laboratory. While it is violently vibrating, they seal it inside an environmental chamber and rapidly swing the ambient air temperature from negative 40 degrees Celsius, which is deep freeze winter conditions, all the way up to positive 125 degrees Celsius, which is significantly hotter than boiling water.
This rapid temperature cycling causes the disparate materials inside the unit, the plastic housings, the solid copper bus bars, the aluminum heat sinks, the fiberglass circuit boards, to expand and contract at vastly different rates.
And they're being shaken the whole time.
Yes. This differential expansion creates immense physical shearing forces on the delicate solder joints and the bolted high-voltage connections. It is specifically designed to rip open those microscopic voids if the AXI scanners happen to miss anything.
And they subject the unit to this combined shaking, freezing, and boiling ordeal for 500 solid hours over 20 days straight while the unit is powered up and functioning.
And the acceptance criteria for the electrical signals during those 20 days is absolute zero tolerance. Throughout the entire 500-hour ordeal, sophisticated monitoring equipment tracks the microcontroller signals steering the high-voltage relays.
Okay, what's the limit?
The specification mandates that there cannot be a single signal drop, spike, or interruption lasting longer than 1 single microsecond.
1/1,000,000th of a second.
Yes.
If the signal drops for 2/1,000,000th of a second because a wire wiggled loose under 3.5 Gs of force at 125 degrees, the entire multi-million-dollar design fails validation and goes back to the drawing board.
And crucially, after the 500 hours are over, they don't just plug it in and say, well, the light turned on, we're good. They perform a destructive physical analysis, or DPA.
What's that?
They take precision diamond saws and physically slice the components open. They place the cross-sections under electron microscopes to prove definitively that the solder layers have zero propagating microcracks, and that the high-voltage isolation resistance separating the 800-volt pathways from the low-voltage logic remains robustly above 100 megohms.
They prove the unit isn't just surviving the abuse, it is shrugging it off.
It has to.
Okay, the final DVP&R test. We've shaken it, we've boiled it, we've pulsed it with power. Now, they bring in something called FPGA Hill fault injection. I know Hill stands for hardware in the loop. How does it validate the safety limits?
In an FPGA Hill setup, the actual physical electronic brain of the car, the microcontroller and its sensing circuits, is attached from the car and plugged directly into a massive field-programmable gate array supercomputer. This supercomputer perfectly simulates the complex electrical behavior of the motors, the battery pack, and the vehicle dynamics in real time. But then the engineers do something deliberately malicious.
Malicious.
They use a dedicated fault injection card to introduce sudden, violent physical hardware failures into the live 800-volt circuit while the microcontroller is attempting to start the sequence.
Oh, it's like a high-stakes video game simulation. But if the computer fails to beat the level, actual lethal voltage destroys the hardware.
Essentially, yes.
The document lists the specific injections. They electronically force a dead 10-ohm short circuit onto the DC bus bar.
Yeah.
They artificially override the sensory pins to convince the computer it has a welded main contactor. They physically sever the data wire connecting to the precharge resistor.
They are meticulously recreating the exact 4 physical root causes we discussed at the very beginning of this deep dive, but they are doing it with live, deadly electrical potential.
And the system's reaction is timed to the millisecond. The acceptance criteria demands that the Dewar-Checker dual-core architecture, the dynamic slope monitoring, the auxiliary pin verifications, all of it must recognize the maliciously injected fault, correctly categorize it as an ASIL D failure, log the appropriate diagnostic trouble code into memory, physically block the massive main relays from closing, and sever the low-voltage drive power.
All within that 60-millisecond window.
Yes. And it must execute this entire sequence within that unforgiving 60-millisecond window.
Because the physical reality of 800 volts colliding with the dead short is violently fast. The current spikes logarithmically almost instantaneously. If the software lags and takes 70 milliseconds instead of 60 to react, the heat generated inside the silicon and the copper bus bars will breach the safety limits.
Right.
The ultimate proof of this test is monitoring the transient temperature rise of the pre-charge resistor during these simulated short circuits. It must remain strictly below its combustion limit. No smoke, no fire, no secondary damage to the vehicle.
So, stepping back and looking at the big picture, we started this conversation talking about a split second of silence when you press a plastic button on your dashboard.
We did.
But we've just spent an hour uncovering the sheer volume of thermodynamic math, physical engineering, microscopic quality control, and intense digital paranoia that exists entirely within that silence.
It is a profound testament to modern engineering discipline. The complexity required to make a massive, potentially lethal electrical power safely accessible and completely boring to the average consumer is just breathtaking.
Boring is the goal, right?
Absolutely. We are asking silicon chips and copper bars to seamlessly manage localized lightning strikes thousands of times over the lifespan of a vehicle without the driver ever noticing.
And the really fascinating thing is that the technology isn't stopping here. In the very last section of the source material, there's a brief, highly technical note about where these engineers are heading next. They're moving beyond physical bench testing and entering the realm of advanced predictive mathematical modeling.
Yes, the Python simulations.
Right. The document mentions engineers utilizing Python-based Foster 3D thermal network simulations.
The dynamic thermal models. Instead of merely relying on testing a physical resistor on a shaker bench until it breaks, they are mathematically modeling the exact three-dimensional thermal blast radius of the heat wave inside the metal casing as it propagates, microsecond by microsecond.
That is insane.
They are optimizing the exact thresholds of the cooling protection delays by simulating different ceramic and aluminum alloy compositions virtually, long before a physical prototype is ever poured in a foundry. It allows them to refine the safety boundaries to incredibly precise tolerances.
It's just mind-blowing. Okay, as we wrap up this massive deep dive, I want to leave you, our listener, with a final thought to mull over.
Yeah.
We've talked extensively today about the extreme precision required to keep an electric vehicle safe. The torque angle servo guns ensuring micro-ohm contact resistance. The 3D X-rays hunting for 1% microscopic air voids in the solder. The end-of-line calibration injecting 800-volt reference signals to zero out thermal drift.
All mandated by ASIL D.
Exactly. Given that this level of microscopic, factory-calibrated perfection is legally mandated to prevent catastrophic failures, think about what this means for the future of auto repair.
The right to repair.
Right. Can a local, independent mechanic ever safely replace a high-voltage part in your garage if the vehicle's core safety relies on robotic tools, X-ray scanners, and calibrations that only exist in a billion-dollar manufacturing facility?
It's a huge question.
If fixing a car yourself means risking a thermal event because you couldn't precisely torque a bus bar, where does that leave the right to repair? It's a massive tension between the right to fix your own property and the uncompromising demands of functional safety. And it's a conflict the automotive world is going to have to reckon with very, very soon.
That is perhaps the most important underlying question for the entire industry's future as we transition to high-voltage platforms.
Something to think about the next time you press that start button and enjoy the perfect silence. Thanks for joining us on this deep dive.